You can hear me. Okay, good. All right, so just to set the stage a little bit, this is a plot of the LIGO sensitivity. So we have the frequency of a gravitational wave that you're trying to detect on the horizontal axis, and then the displacement noise. So the blue curve is initial LIGO. At high frequencies, that's quantum noise that's limiting it, the shot noise. Then there's thermal noise and seismic noise at lower frequencies. So for enhanced LIGO, the quantum noise limited sensitivity was increased by turning up the laser power, which is the standard way to reduce the shot noise. Advanced LIGO is going to turn up the laser power even further. So right now, we're in the time between enhanced LIGO and advanced LIGO. So the detectors have been taken apart and they're being upgraded. So advanced LIGO will have a laser power that's sort of at the limit of the available technologies. And so if we want to reduce the quantum noise even further after that, we have to think of a different technique, and squeezing is one promising way. So we were able to do an experiment after the end of enhanced LIGO. There were 2 interferometers at Hanford. The upgrade began on one of them, and the other one was preserved so that we could do this test. So I'm going to start off with just an introduction to interferometers and quantum noise in interferometers. Then I'll talk about how we can use squeeze states in interferometers and how we make squeeze states. Then I'll show you the results from H1 of a sensitivity improvement. I'll talk about a potential noise source that we investigated, and then what was limiting the amount of squeezing that we detected. Okay, so you can hear me? Okay. So the quadrature, we need to understand, we need a quantum picture of the field if we want to understand the quantum noise in the interferometer. So just like a classical field, we can write the field as a sum of 2 quadratures. There's a real and imaginary part, or the sine and the cosine part. So we can plot this in the plane of x1 and x2, these 2 quadrature amplitudes. And this phasor rotates at an optical frequency, but we're looking at it in the rotating frame so that it's still. And now, oops. All right. These quadrature amplitudes are, instead of being classical numbers, they're operators. So there's a variance in each of them, and there's an uncertainty relationship between those 2. So this uncertainty relation puts a minimum on the area of that purple ball, the noise ball. So the cartoon of the state I've drawn here is a coherent state, and that's a good approximation to the light that comes out of the laser. So if you rotate these 2 quadratures, you can identify one of them with phase noise and the other with amplitude noise. So when the coherent amplitude goes to 0, the variances remain, and we end up with a vacuum state. So everywhere that classically you'd think of no field, there's these vacuum fluctuations, and we need to understand their effect on the interferometer to understand the quantum noise. So here's just a cartoon of the interferometer. There's 2 4-kilometer long arms. Each arm has a Fabry-Perot cavity that just increases the effective length of the arm by recirculating the light. There's also a power recycling mirror that increases the laser power effectively by just sending the laser light that would exit the interferometer back in. And this PD over here at what we call the antisymmetric port is where the gravitational waves are detected. But we can understand the quantum noise just by thinking about even an even more simplified thing, which is just a simple Michelson near a dark fringe. So we have laser light that comes in at the symmetric port. The arm lengths are locked so that most of that light goes back towards the symmetric port, and only a small amount comes out to the antisymmetric port where the gravitational waves are detected. So there's an unused port to that beam splitter. So of course there's vacuum fluctuations that enter, and those reflect off the interferometer, and they impose their noise on the small coherent amplitude that's coming out at the dark port. So that's what's responsible for all of the quantum noise in the interferometer. So that means at high frequencies there's shot noise. At low frequencies it's radiation pressure noise. So the shot noise comes from random photon arrival times, so from phase noise, and then at low frequencies, the amplitude noise moves the test masses, so that causes a radiation pressure noise. So it was understood over 30 years ago, as Rana said, that this would limit the sensitivity of gravitational wave detectors. So squeezing was proposed as a solution that long ago, and now we're finally able to use it. So what's squeezing? We have the uncertainty relation that just places a minimum on the area of that ball, but not a minimum on the uncertainty in either quadrature. So we can reduce the uncertainty in one quadrature at the expense of increasing it in another quadrature. So there's two numbers you need to describe the squeezing. First, there's the squeezing factor R, which tells you how strongly squeezed that ellipse is. And then second, there's a squeezing angle, which tells you which quadrature you're squeezing. So we can arrange the quadrature so that we reduce the phase uncertainty, and then we call it phase squeezing. And then we call the increase in noise in the other quadrature, we call it anti-squeezing. So we have phase squeezing and amplitude anti-squeezing. You can do it the other way around. Or if you have no coherent amplitude, this is what we actually do. We make a squeeze state with no coherent amplitude, so we call it squeeze vacuum, or vacuum squeezing. All right. So we can use this in the interferometer. We actually don't have to make any changes to the interferometer itself. We just take those vacuum fluctuations that are entering at the dark port, and we put a squeezer, something we call a squeezer, in the way, so that it passes through this cavity, they become squeezed, and when they reflect off the interferometer, the noise that they impose on the gravitational readout is reduced if you control the squeezing quadrature correctly. So this is a projection for advanced LIGO. I forgot to say before, but there's no thermal noise, there's no seismic noise in this plot, so it's only quantum noise. So at high frequencies, we reduce the shot noise. This is 6 dB of phase squeezing. So we have a factor of 2 reduction in the shot noise, and there's an increase in the radiation pressure noise. This is exactly the same as if you had increased the laser power by a factor of 4, but without any of the thermal effects or the classical radiation pressure effects. Another thing that you could think about doing with squeezing is if you don't want the degradation at low frequencies, you can do frequency-dependent squeezing, where you inject phase squeezing at high frequencies and amplitude squeezing at low frequencies, so you get a broadband improvement through the whole spectrum. So this is the squeezer. We have our squeezer, and it's a crystal squeezer, which is a standard way of making squeezing that uses nonlinear optics to create correlations between symmetric sidebands. So to explain that, first, we'll just talk about side noise in the sideband picture. So these top two plots, we have frequency on the x-axis, and then these black lines are single frequency components of the field. So the carrier is the large black line in the center, and then there's two symmetric sidebands that rotate at their sideband frequency. So that frequency is the frequency of a gravitational wave that we're trying to detect. So on the left side, these two sidebands are out of phase, and that means that they add phase noise. So the red arrow is the sum of all three of these. Oops. You can see that it was wobbling back and forth in phase. Sorry. There we go. So in the plane of x1 and x2, we just have the sidebands that rotate around the carrier, and you see that we're adding phase noise on the left, but we're not adding any amplitude noise. And then on the right, the two sidebands are in phase. That means that they add amplitude noise, but they don't add any phase noise. So this is just classical amplitude modulation and phase modulation. Okay, so we want a quantum description of the light, so we need to account for the vacuum fluctuations, which are at every frequency. So we have these uncorrelated random fluctuations at every frequency, and we add them onto the carrier light, what we end up with is a Gaussian distribution of noise that's equally distributed in the two quadratures. And this is just a coherent state. So the picture on the right is just a cartoon, the same cartoon of a coherent state that you saw before. Now if we make correlations between some of these sidebands so that they're more likely to be in phase than to be out of phase. They're more likely to add amplitude noise and they're less likely to add phase noise. So we get our probability distribution is an ellipse with a smaller variance in phase and a larger variance in amplitude. All right, so this is just a picture of our squeezer, just showing you some of the important parts. We have a laser that's locked at the frequency of the interferometer laser. And then there's a second harmonic generator where the frequency of that laser is just doubled so that it becomes green light. And the OPO is the cavity where those correlations are created. And then so a squeeze state exits the OPO, and we can either send it onto our local homodynamic detector, which we use to characterize the performance of the squeezer, or we can send it into the antisymmetric port of the interferometer. So what's actually happening in the OPO is that we have a nonlinear crystal. That means that the displacement field depends, it has a component that depends on the electric field squared. So that means that fields at different frequencies can exchange energy. So we have two fields. We have the green field, which we have annihilation and creation operators for that we call B. And then we have the red field, which we have A and A dagger annihilation and creation operators. So in the OPO, there's these two. This is the Hamiltonian that describes only the interactions between the fields. So each field has the normal harmonic oscillator Hamiltonian. So kappa is just a number that describes the parameters of your experiment, the strength of the interaction. And then there's these two interactions that happen. So in the first one, you annihilate, you destroy a green photon, and you make two red photons. And the second one, you take two red photons and you make a green photon. So in the OPO, we're careful not to send any red photons in. We send no photons in at the interferometer's carrier frequency. And we have a large coherent amplitude of the green that's at twice the interferometer's frequency. So we know that the two red photons in this interaction are symmetric sidebands around the interferometer's carrier frequency. And since we tune the temperature of the crystal carefully, we know that energy is going to be conserved in that interaction. So so that's why we know that they're symmetric sidebands. Yeah, so if the vacuum field is propagating through this crystal, then the phases of the red photons, as they interact with the green, they're going to become correlated. So we have to control the squeezing quadrature. So I'm not going to talk about this, but it was just that we thought about, before we built the squeezer, we thought about how we would control the phase noise and how phase noise would propagate through our table. So we modeled it, and then we built the squeezer. We saw that it worked well enough for our experiment, and so we took it to Hanford and installed it. So that's a picture of the squeezer. Behind it, you can see the beam splitter, the chamber where the beam splitter is. So our goals at Hanford were to demonstrate that squeezing doesn't add any extra noise anywhere in the LIGO band. So the reason we did this at LIGO instead of, there have been experiments done at other interferometers like GEO. They've had squeezing. But we wanted to show that in a very sensitive interferometer, we can do squeezing without adding noise. Then, of course, we wanted to show that we could actually improve the sensitivity of the interferometer. We wanted to understand some of the potential noise couplings so that we could plan for an even more sensitive interferometer. And then we wanted to understand what was limiting the amount of squeezing we measured so that we could plan to measure more squeezing in the future. Yeah?
This was a frequency dependent?
Frequency independent.
Frequency independent.
Yeah, we just, I can go back and with enhanced LIGO, there's no radiation pressure limited part of the spectrum. So the seismic noise, maybe I shouldn't have gone back. The seismic noise is so large that the increase in radiation pressure noise didn't matter. Oops, sorry. All right. So this is just our layout for our experiment. The blue box is the squeeze light source, and we send the light in, well, the vacuum, the squeeze vacuum, in through a Faraday. We use the interferometer's output Faraday as a circulator to send the squeezing in. It bounces off the interferometer and comes back through that Faraday again. And then it passes through the output mole cleaner, and then we detect it on the gravitational wave readout PD. So here's one of our results. So the black trace shows you the sensitivity without squeezing, and then the blue trace is with squeezing injected. So the first thing to notice is that there's no frequency in this plot where we added noise to the spectrum. So also, of course, at high frequencies, we improve the sensitivity. So the in-spiral range between the black trace and the blue trace is improved by about 1 megaparsec. The in-spiral range is heavily weighted towards low frequencies, so all of that improvement came from below 1 kilohertz. The red trace.
How many dB is this?
So this one is right around 2 dB. It's like, yeah. Which most of the results we have were right around 2
Just
dB.
linear? I mean, 2 dB of squeezing gives you 2 dB of sensitivity?
Oh, yeah, so, yeah, that's what. Well, I'll talk about, the squeezing we injected was a lot more than 2 dB, but I'll talk about how we lost it. So the red trace is the best sensitivity that was seen during S6. So you can see that at high frequencies, where our sensitivity that we started with was comparable to the best during S6. And so our squeeze traces shows you that we had the best broadband sensitivity that's ever been achieved so far in a gravitational wave interferometer. You can see at low frequencies that the best curve was taken at a time when the seismic noise was unusually low, and we took our data at a time when the seismic noise was unusually high, but we weren't adding any noise at those frequencies. So this is a result from the interferometer operated at 8 watts. You can see this is plotted as a ratio of the noise without squeezing to the noise with squeezing. You can see, so at high frequencies, we have about 2¼ dB of squeezing. And then there are frequencies where the interferometer is dominated by technical noise instead of by quantum noise, so we don't see as much squeezing at those frequencies. Then below about 1 kilohertz, the thermal noise starts to become more important, so the squeezing just slowly rolls off. But we can see some improvement in the spectrum, almost down to 100 hertz. So it was nice to see that we could see improvement down to those low frequencies, because one of the things that we were most worried about doing this experiment is that we would have acoustic couplings that at a couple of 100 hertz, which could actually degrade the sensitivity of the interferometer. So the acoustic, we saw that we didn't degrade the sensitivity, but we wanted to be able to predict for a more sensitive interferometer where the noise that we added would be. So we investigated a couple of acoustic couplings, but the one I'm going to talk about is backscatter. So the way this coupling works is that there's a little bit of imperfection in the Faraday. So there should be no light coming towards the OPO, but there's a small amount of light that comes out of the interferometer and towards our squeezer. So we put a Faraday in that should reject most of that light, but there's still about 3 microns that come out towards our OPO. So if that light resonates in the OPO, it can be backscattered by imperfections and surfaces inside the OPO, probably most likely the crystal surfaces. And then it will head back towards the interferometer. And then it creates a, yeah? Okay. It creates a spurious interferometer that senses the motion between the OPO and the interferometer instead of the motion of the test masses or the differential arm length. So there are 3 ways to reduce this backscatter noise. The first is to improve the optical isolation. The second would be reducing scattering sources on the squeezer table itself. This is why we chose a traveling wave OPO cavity instead of a linear cavity, because it should be immune to first order. It's immune to backscatter. And then the last option is reducing relative motion between the squeezer table and the interferometer. So this is a result. You can see that in the bucket, we're at least a factor of 10 below the noise of the interferometer. We did this by shaking our table so that we increase the noise above the sensitivity, and then we could just compare to the ambient noise, the normal motion of our table, and predict where the noise should normally be. So for advanced LIGO, you're going to have higher power and better sensitivity, so you probably want another factor of 10 or so reduction in this noise. I think a good way to do that would be to reduce the table motion. The PSL tables, if you compare the PSL tables, the pre-stabilized laser tables, to our squeezer table, they should have about a factor of 10 less motion because of the acoustic enclosure and because of the carefully designed table legs. Another improvement would be to get better performance out of the Faraday isolators. We measured about 10 times better performance in the lab than we got actually when they were installed on the interferometer. So if you had 10 times better performance, you would get a factor of 3 reduction in the backscattering noise. But the bottom line is that without really any major design changes to our squeezer, it would be compatible with advanced LIGO sensitivity for backscattering. So even though backscattering wouldn't be a problem, if you're going to install a squeezer for advanced LIGO, you probably want to see more squeezing, maybe 6 or 10 dB of squeezing. So the things that can limit the squeezing that we saw are technical noise, which I'm not going to talk about. It just masks the squeezing because it's not quantum noise. Then there's losses in the detection path, and then phase noise of the squeezing angle. So losses destroy squeezing because, well, every loss you can model it as a beam splitter with some transmissivity eta loss. For quantum beam splitter, you always need to think about what's coming in from the unused port, and in this case it's vacuum fluctuation. So we're adding something with a high variance to something with a small variance, so the result is something with a larger variance. So here's a plot just showing how losses degrade squeezing. So on the horizontal axis, there's the generated squeezing, and then on the vertical axis, there's measured squeezing. So for 5%, we generated about 10% squeezing in our, 10 dB squeezing in our OPO. If there were only 5% detection losses, you would have over 7 dB of measured squeezing. If you had 50% losses, you would be just over 2 dB. So this is the way that we characterize. H1 is a squeezing detector instead of, we thought it was a gravitational wave detector, but we wanted to characterize it as a squeezing detector. So we turn up the nonlinear gain. That's what's on the horizontal axis here. That means basically that we're making more anti-squeezing for the same amount of squeezing. And we don't want to use squeezing to get a measurement of our losses because there are a couple of ways to destroy squeezing, but anti-squeezing is really only sensitive to losses. So we make a fit to those points. At each point we measured the minimum noise and the maximum noise that we can make, so we get a fit for the anti-squeezing. And this plot has about 60% losses in the detection path, but the losses depended on interferometer alignment. So Some days we saw about 55% losses. It was usually between 60 and 55% losses if things were well aligned. So that's kind of a lot of losses. So where does that all come from? First of all, we have 3 passes through Faraday's in our injection path, so that adds up to about 20% losses. Then we also have another 20% losses in transmission through the OMC. We also had mode mismatch. So we measured our mode mismatch with one of the interferometers. The input test masses misaligned, so the interferometer was unlocked. And we saw we had about 20% mode mismatch. But we know there's a big uncertainty on that measurement because we know for the interferometer's mode match, there's about a 30% difference in the mode matching that you measure that way and the mode matching that you measure with the interferometer locked in at high power. So we infer from our total losses the mode mismatch, and then we get about 30% mode mismatch. So if you wanted 6 dB detected, you would have to reduce all of these losses down to something around 5% to get your total losses under 20%. So phase noise is the other thing that limits the amount of squeezing that we measure. This just means that the squeezing angle is jittering, so this ellipse is mixing some of the anti-squeeze quadrature in with the squeezing. This plot just has squeezing angle on the horizontal axis and then variance on the vertical axis. So we lock to the minimum, to that bottom of that dip, and so any variation, no matter what frequency it's at, will add noise to the spectrum. And the more squeezing, the higher the level of the squeezing that you have, the steeper that dip gets, so the effect of phase noise becomes higher. So this is a similar plot with generated squeezing on the horizontal axis and measured squeezing on the vertical axis. So if you had 10 dB of squeezing that you generated, and I'm assuming about 20% losses, so that you would be able to measure around 6 dB. If you had no losses, no phase noise, sorry, you could measure about 1 dB more squeezing than if you had 80 milliradians of phase noise. But if you look at higher amounts of generated squeezing, then the effect of the phase noise becomes more important. So phase noise wasn't really limiting our ability to detect squeezing, but we wanted to account for all the phase noise that we saw and make sure that we understood where it came from. So we had about 1.6 milliradians of phase noise just from the RF sidebands, which was insignificant for us. We had an upper limit of 22 milliradians on the phase noise that came from sources on our table. So these are the things that we modeled in that control diagram, like laser phase noise and the length noise in the cavities. However, our phase noise budget didn't really add up, we saw. So there was a third source of phase noise that we hadn't expected. When we saw that our budget didn't add up, we decided to investigate the phase noise by going to really high nonlinear gains. So what that does is we create a lot of anti-squeezing for the same amount of squeezing. And so the anti-squeezing is mixed in so strongly that actually our squeezing is actually anti-squeezing. We're actually adding noise even when we're squeezing. And that's very sensitive to the amount of phase noise that we have. So what we saw is that changing the alignment changed the error point of our squeezing angle loop. So that means that beam jitter will add phase noise. So the difference between the green point here, where we have almost 2 dB of noise added to the interferometer, and then the blue point, where we have around 37 milliradians of phase noise, is just that the alignment of the interferometer was changed, and then we readjusted our error point. So one thing that probably should be done is to implement an auto alignment system for a squeezer, and that would certainly help to keep the phase noise more stable, because it would keep the relative alignment more stable, and hopefully it could also reduce the beam jitter, which would reduce be able to reduce the phase noise. So just to look kind of towards the future, this is a plot showing the amount of squeezing that you can measure for certain phase noise and a certain percentage of losses. So for the H1 test, we were up there between 55 and 60% losses, and we had around 37 milliradians of phase noise at best. So that put us just over 2 dB of squeezing. So if you want to measure, say, 6 dB of squeezing for advanced LIGO, you could accept the same level of phase noise, but would just have to work to get the losses down below 20%. But if you want to measure, say, 10 dB or maybe even more, you have to worry about both losses. You have to really reduce the losses, and you have to reduce the phase noise. So this is just for Rana. I guess he wanted to see how could you make 20 dB of squeezing, and I guess that if you get your phase noise down to, say, 1 milliradian, which could be challenging, I think, you would have to get your losses down to something like 0.75%. So I think both those things could be challenging. But, so just to summarize, we saw 2 dB of squeezing in H1. We saw that there was no extra noise added at any frequency in the spectrum. We saw some benefit from squeezing. With the interferometer at full power, we saw benefits from squeezing down to around 150 hertz. And then we saw that backscatter shouldn't be a problem for using squeezing with advanced LIGO. We learned that beam jitter causes phase noise because of the way that we sense the squeezing angle. And the most important lesson, I guess, is that losses need to be reduced if you want to see high levels of squeezing in the interferometer. So I just wanted to thank everyone who worked on this project. There was a lot of people who worked on it. Especially, I want to thank my advisor, Norgis Mavavala, and Lisa Barsotti, and Danielle Sig. Okay, and thank you for your attention. Does anyone have any questions?
I wonder, why did you choose a particular squeeze angle control thing that you have instead of using this noise locking stuff?
Yeah.
I would have guessed that you can dither the auditor angle at tens of kilohertz and then have something like a 1 kilohertz bandwidth with a squeeze angle. And then you should be immune to a lot of these error point offsets in this line of things.
Yep. Yeah, I think that might be a good idea. I guess the reason, that always adds some phase noise, but I think it probably could be less phase noise than what we got from the beam jitter. And then we started off hoping to have high bandwidth in that loop, but we saw that you can't really have high bandwidth in that loop because of the arm cavity resonances anyway. So yeah, I think that noise locking might be a good solution. But with noise locking, you always, I think it might be hard to get down to that 1 milliradian of phase noise. I'm not sure. Because you'll always have some amount of phase noise from the RF sidebands, and then you have to add your dither onto that. So.
Can you go back to the table of losses that you showed us? All these losses happen before the prepared light is injected into the interferometer.
Oh, so
Losses in the interferometer limit at all?
actually, so if I just go back to there we go. So most of those losses are actually, you mean You mean from reflection off the arm cavities and the mix? No.
The interferometer is not a perfect device.
Yeah.
So even if you were able to make all your losses zero, wouldn't that limit the performance, or is that not important once you've actually mixed it with the carrier light on the interferometer itself?
Yeah, so we estimated that there would be about 2% losses from the interferometer, but because of the losses we had were so much higher than that.
60.
Yeah, I don't really know.
Thanks.
Mm-hmm. Right. So,
This question back there? You're on mute.
What are the plans then for squeezing in advanced
well, not in the baseline for advanced LIGO. So there are people at MIT who are working on a filter cavity so that they can do the frequency-dependent squeezing.
Is that hard? Or have there been any demonstrations of frequency-dependent squeezing?
Yeah, it's been done before, but I think not really at frequencies that are useful for LIGO. Yeah, I think so you bounce your squeezing off of a filter cavity, and it's been demonstrated before that that works, but just if you can get a filter cavity with low enough losses to have a low enough bandwidth to be useful for LIGO is, I guess, the question.
So it seemed like most of the loss is dominated by the output mode cleaner in terms of mode matching and losses in the mode cleaner.
Mm-hmm.
Is there some sort of difficult technical challenge there, or is it just we could just make better output mode cleaners?
Well, I think the output mode cleaner at some point had much lower losses, like 5% losses.
Was it, so the one that you quote, is that from the original H1 or the L1?
Yeah, so what Jamie's talking about is that we originally had about 50% losses, and then we replaced the output mode cleaner.
Okay, so this was the better one.
Yeah, but we still didn't get the performance that the best during S6. So that.
Did you not have a mode matching telescope as part of your system?
We did.
So in principle, if you had the time, you could have tweaked the mode matching to get it better? Was that the best it could possibly be?
No. Yeah, I think it could be better. Part of it is that we just ran out of time. I think that if you spent more time, so we did our mode matching with the single bounce with one arm misaligned, but another way to do it would be to look at, if you go to really high nonlinear gains, and you look at the anti-squeezing, and then you just, yeah, or to make the most anti-squeezing that you can get. We tried that on the last day, but didn't really have
the loss that you quote it's just mode matching from the IFO into the OMC, right?
No, so there is a mode mismatch between the interferometer and the OMC, which is kind of similar. I think it's around 30% as well. I don't quite remember, but that's the mode mismatch that we inferred from the level of anti-squeezing that we saw. So that's the mode mismatch from the squeezer into the OMC.
So which one was more important? Which was bigger in this case? Was it the mode matching from the IFO to the OMC, or the mode matching from the squeezer into the IFO? The mode matching that mattered for us was from the squeezer into the OMC. I think since we were only reducing the shot noise, I think that the only mode matching that matters is from the squeezer to the OMC, because that's just the amount of squeezing that ends up on your gravitational wave readout PD. But if you want to see, I think. Why do you say the squeezer into the OMC? Because if you're matching it, the mode matching is from the squeezer into the rest of the interferometer, right? And then
and that determines what the interferometer determines what the mode matching is into the OMC?
Well, you know, we just bounce off. So only at low frequencies would this squeezing actually go into the arm cavities, because the arm cavity pull is like 100 hertz or something, so it's very low. So for the most part, our squeezing is just reflected off of the ITMs.
Oh, right, okay, yeah, that's
And go back to your loss budget that you showed for the target. Are there designs in hand that could achieve those very low numbers, or does that require an optanium?
So I think that the 6 dB, yeah, we were talking about this earlier. I think the 6 dB should be achievable. I guess that Ron talked to people at the LVC about Faraday losses, and that should be reasonable. Of course, mode matching, something that, you know, we have to get better at that anyway, and I think with time we can get better at it, right? And then the OMC transmission, certainly 5% is reasonable, because that was achieved during S6, so it should be reasonable. But if you want to see, say, 20 dB, I'm not so sure if that's, yeah.
5% transmission, that was achieved during S6?
I think 94% or something transmission. Yeah. Yeah. So,
Oh, I didn't appreciate this. So even the L1 OMC degraded
yeah.
to what it was in S6?
Yeah.
Was this one of the University of Florida Advanced LIGO Faradays?
This is the advanced. So we had our Faraday that we put in our injection path was the enhanced, or the initial LIGO Faraday from H2, and then we used the advanced LIGO output Faraday, which I think was made here for the Faraday that we passed through twice. And our losses might have been worse in that Faraday because the advanced LIGO beam size is going to be smaller, and so we had too big of a beam going through that. Any other questions?
Great. Thanks, Sheila.
Okay.